So how are we gonna factor this? And put all your phones away, please. I want to, I'm really excited to teach you this stuff. We're getting into some stuff that's like next level stuff, a little more serious. It's more applicable. You got to get excited about this. I promise you, this is more important. Okay, this reflects. I mean, we talk about this stuff even in calculus a little bit. About polynomials and properties of polynomials. Let's take a little different approach here. If we were going to solve this, I'm going to give you just a little heads up into where we're going in the future. If we're going to solve this equation, what would we do? Okay, we could factor it. Okay, that's plan A. How would we approach that if we're going to factor it? What is the pattern? It's the only pattern it could be. Say it again. Well, okay, this would be not the plus, this would be the difference of cubes pattern, right? So let's write that one down. So if we have something like a cubed minus b cubed, what's the factoring pattern that goes with that? Okay, so the first one, remember, we've just got a's and b's and a squareds and b squareds and a's times b right there. In the first linear factor, we'll just leave the signs out. Let's just put all the terms in. There's the small linear factor. Here's the quadratic factor. So that's the one with a squared. What's the next term? ab. And then, okay, so now let's just populate that with the signs. What goes there? Minus, and that's always plus, right? Okay, so then we just need to turn this into, we have to see if this applies. We can addition this and see if it works. Is it a difference of cubes? Can I write this first term as something cubed?
2x.
Okay, cube root of 8 is 2, right? So it would be 2x, and then 27 is just 3 cubed. So that's my A, that's my B, right? So then all I've got to do is just plug the results into this pattern and do a little simplification. So the first term, or the first factor is then just going to be A, which is 2x minus 3. And the second factor is going to be, let's see if we can do this in one step. What's the first term going to be here?
4x squared. 4x.
Okay, because it's the quantity, it's a squared, and a is 2x. So I've got to actually square that out, distribute the exponent. What's that? Oh, okay, all right. Just want to make sure that we're doing a little touchy about these things right now. So what's that become?
4x squared.
4x squared. So we'll just skip right to 4x squared plus a times b. So 6x, 2x times 3 would give us 6x, and then plus 9. Okay, so here's my question for you. This is the part that's pretty cool. Remember, all we're doing is solving an equation, right? So now I've got these two factors. What would I do to solve this thing? So we have one solution right here, don't we? What's that solution going to be? Can you tell me? How'd you get that? Good, because if this is set equal to 0, and you can do this in your head, there's always going to be 2 steps at the most. We're just going to add 3 to the other side and divide by 2, right? So we get one solution is x equals 3/2. My question is, what about this other factor? Okay, so try to factor it out. Yes, Sam?
So I'm confused about just the middle term real quick.
Mm-hmm.
In the second quantity.
This one right here?
So isn't it 2 times a?
No, it's not. That's different. You're thinking of, I know what you're thinking of. You're thinking of this pattern. You're thinking of the pattern a plus b squared equals a squared plus 2ab plus b squared, right?
So is it just AB?
It is. It's just ab. So in the sum or the difference of cubes pattern, and we could actually write it this way. This is kind of a way you'll see sometimes. It's a good way to do it. Like if we put a cubed plus or minus b cubed, I could put the plus on top and the minus on the bottom. And then when there is a difference in signs, when the signs switch over here, the top sign goes with the top sign, the bottom sign goes with the bottom sign. Does that make sense? So we could sort of combine both of those formulas in one. But in both cases, thank you. But in both cases, the term in the middle here in this quadratic factor is just AB. There's no 2 in front. Okay. All right. So back to the question. Then we've got this broken down to the product of these two factors, and the suggestion is, can we go ahead and just keep going with this? Okay. Well, we could try. But even if we try to do like bottoms up, for example, right? To know if bottoms up is going to work, we have to see if we can find magic numbers, right? We'd want to see if we can find factors of A, C, so factors of 36 that add to B. We have to be able to do that in order to factor it, right? Conveniently with integer factors. Are there numbers that do that? Numbers that multiply to positive 36 and add to 6. Not going to happen, right? Okay, so we know it's not going to factor. Does that mean there are no solutions necessarily? Because when we solve a quadratic equation, and really what we're doing now is we're saying, okay, we've got this other quadratic factor that we're going to set equal to 0, right? So let's go ahead and just write that equation down. It didn't factor, but maybe we could solve it another way, right? Now we'll just go back to Module 3 stuff and solve that. Well, how would we go about solving that problem? Quadratic formula, right? When we do the quadratic formula, remember where we want to always start is with the discriminant part, though, right? And then we'll just fill in the blanks later if we need to. How come? Yeah, because we're looking for real solutions here, right? We could, if we're looking for all solutions, then we just keep going, right? And we might get I's in our answer, and that's fine. We're not going to do that for now, though. For now, we're just looking for real solutions, okay? So, if we were to set up then the discriminant, we're going to get the square root of b squared, right? So that's 36 minus 4 times 9. Well, what do you know already? That's we're going to get 36 minus a bigger number. What are we going to get? We're going to get a negative number, right? So we can stop, right? We know that we're not going to get any real solutions. Okay, the question is that an accident? No, it's not. It's not. It's always going to be that way. So when you use any of the cube factoring patterns, sum or difference, what you end up with here is a linear factor, which is always going to give you a solution. And you end up with what we call an irreducible quadratic. I don't think our book uses those words, but I want you to know that. What that implies is that it's not going to give us any real solutions. It's always only going to give us imaginary solutions, complex solutions with imaginary parts. If you think about what the graph of a cubic function looks like, think about the different possibilities. Cubic functions can either have 2 turning points or no turning points, right? We could have a cubic function that does something like this, which either comes down and crosses or maybe doesn't cross, right? But there's 2 distinct turning points here. Or we can get cubic functions that do something like this, that don't turn, right? Which one do you think this is always going to be? When we start with a difference of cubes or a sum of cubes. If you were to graph it. Yeah, it's going to be the one that only turns. It doesn't turn at all. So you're only ever going to get one real solution out of this. Okay. Does that make sense? Okay. Okay. Oh, I was going to show you something. Okay. So something else we can do with that. I just want to give you a little heads up. This is a little out of order, but you guys aren't normal students, so I'm just going to throw this in now. Theoretically, what should we be able to do with this equation also? Based on a rule that I gave you earlier in the year, we shouldn't have to factor this. We should be able to, we can point to a single x, so we should be able to isolate it, right? Okay, so what do you suppose, and I'm not going to go into too much detail with this because we're going to talk more about this in module, I can't remember, 7, I think, or 8 or something. I can't remember when it is exactly. I think it's 7. What are the steps I'm going to go through to isolate x? add 27, divide by 8, okay? Right, I'm just working backwards through order of operations, right? So first I add and subtracted, then I multiply or divide, and then finally a cube root. So x is gonna equal the cube root of 27/8. Now we'll talk much more about this in the module where we cover it, but do we need a plus or a minus or not? And you wouldn't know. Do you think we do? No, we don't. How come do you think we don't? Because it's an odd root. Yeah, when it's an odd root, you don't need a plus or minus, and so we would just get a single answer out of that. And what is the cube root of 27/8, do you suppose? Yeah, it's gonna be the cube root, and we'll talk more about this later. Cube root of 27 over the cube root of 8, which is 3/2. We get it that way also. Which is a better way to do it? If you're looking for real solutions, that way is. It's a lot easier, right? If you want to find all solutions, and I am going to at some point have you guys find all solutions, real and all the complex solutions, then you would have to factor it, wouldn't you? Because in order to get those imaginary ones, we'd have to solve this quadratic equation to get Heisenberg answer, right? Okay, so just I want to wrap a couple things up from yesterday. What I want to show you today, ooh, what's that? Did I hit the, oh my gosh, did I? Oh, there it is. There we go. Right? There we go. Okay, so, yeah, let's look at stuff like this. How we could solve an equation like that? So we're gonna have to factor this, right? Now this is a whole different level. This has got, this is a cubic function. It's got 4 terms. You can't do as much stuff with cubics as you can with quadratics. Quadratics, you can always fall back on the quadratic formula. There isn't a nice, simple cubic formula that allows us to find the solutions of a cubic equation, unfortunately. So we've got to somehow try to whittle this thing down. And there are that's what we're going to be taking a look at, for a while. Actually, I know the next module the next lesson is going to be about some other tricky ways we can kind of trick some solutions out of this. But for now, we're just going to look at how we can factor it. So one approach we could do is called factoring by grouping. Okay, and this is a pretty common approach. I do want to preface this by saying that factoring does not always work, right? I mean, it really doesn't always work. There are going to be lots of cases where you simply can't solve a polynomial equation by factoring. You have to do something else. Ultimately, in the real world, how would we solve this? Like if you're working as an engineer, which I've done. Yeah, you're not gonna think. You just throw it in your graphic calculator or throw it into a computer algebra system and just ask it for solutions. I mean, you're really not gonna be oftentimes doing this kind of algebra on a daily basis when you get up to big polynomials like this. But how could we do this? By using a technique called grouping. All we're going to do when we factor by grouping is we're going to group the terms into 2 pairs of 2 usually, and see if we can either factor out a common factor, or we could have a common leftover factor. Okay, and by leftover, I'll explain what I mean in a second. So let's say we take the first two factors. If I were to factor out the greatest common factor of the first 2 terms, what would that be? X squared. So we're going to make the greatest common factor part, I'm going to make blue. So we could split this apart into x squared times the leftover factor, what? Minus 1, right? Everyone's okay with that, right? Give me a 1 to 5 on that. Everybody, makes perfect sense? It feels like they could do that? Okay. So here's my leftover. Let's look at the other side. Now I've got this plus sign in the middle. On the other side, well, is there any greatest common factor? There is not. I already have the factor x minus 1. So if I treat that as my leftover, what's the factor, what's the coefficient? What's being multiplied by it? 1. Okay. So now look what we've done. We've got this to a point where I have a common factor in each of these two terms, right? I split this up down the middle into a factored term on the left and a factored term on the right. What is the common factor of those two terms? And once again, let me label these. This is, we'll call this term 1, and that's term 2, because terms are the things that are being added or subtracted. Does everybody agree that in this statement up here, I've got how many terms? 4. In this statement here, I've actually got 2, right? And so what is the common factor again of each of those two terms? X minus 1. It's the quantity x minus 1, right? So if I factor the x minus 1 out front of each of these two terms, what am I now left with?
Squared plus 1.
Yeah, now I've got my x squared, and here's my plus 1. Does that make sense? About that. It's factored, right? And the whole point here was to solve an equation, let's say. And so what would we find at that point? Am I going to be able to factor this any further? Not going to, right? Because what pattern is it?
Sum of squares.
Sum of squares, which is a non-pattern, right? That one doesn't exist. So we can't factor that one. What's the solution from the first factor?
1.
Yeah, x equals 1. And then what do you suppose, are we going to get any real solutions from that one? No. If something doesn't factor because it's irreducible, it's not going to give us real solutions. And we can show that pretty easily, right? If we set that equal to 0, well, I'd have to subtract 1 and then square root, and I'm going to get i's in there, right? So we can already see that one's, just cross it out, it's not going to give us any factors, right? Make sense? Okay. Okay. So that's where we'd have to stop, right? Couldn't go any further. Try that one. Try factoring that by grouping. All right, so if I group this, let's take the first two terms. What's the greatest common factor of the first two terms? X cubed, okay. So out of these two, we can pull an x cubed, leaving us with what? X plus 1. Okay, plus, and then we're in the same boat as last time, aren't we? We've got this x plus 1, and so if I want to write it, there is a coefficient of 1 out front, right? So then what do I end up with if I've grouped the two, now what if I factor out the leftover common factor?
X plus.
Times.
X plus 1.
Okay, so can I go further?
Yes.
I can't, because this is a sum of cubes, isn't it? Right, so I can split this one up into what?
Plus 1 minus x squared minus x squared.
Okay, good. So we can recognize that A is x and B is 1. We'll use that pattern, right? So A plus B, A cubed plus B cubed is A plus B times A squared minus AB plus B squared. And then I've got my x plus 1 out front. Okay, so we're done, pretty much. Except there's one other thing we could do to this. How could we write this in a way that's a little more simplified and compact?
X plus 1 squared.
Yeah, look, I've got an x plus 1 times an x plus 1. And so those become x plus 1 squared. And then I'm left over here with x squared minus x plus 1. If we were solving this, how many real solutions would we get? How come? Okay, but what did we say in a sum or difference of cubes? What do we always say about the quadratic we get out of that? It's gonna have a negative discriminant. It's irreducible, right? So we're gonna get no real solutions from this guy or this guy, right? So the only real solutions are gonna come from these two, but they're the same. So really I only get 1, 0, don't I? One real solution.
Where did you get the x squared minus x plus 1?
From this pattern. We just used the pattern a cubed plus b cubed equals a plus b times a squared minus ab plus b squared.
Okay.
Okay? Does that make sense? Okay? All right. So then I'm going to skip this one for a second. I'll show you one more of these. This is kind of a tricky one. These are, honestly, these probably, maybe as a challenge question, I'll throw you one of these to do or something. But these are a little bit harder. What do you notice about this one? Not really going to work, is it? It's not going to work if we do two groups of 2. Because if I extract, there is no greatest common factor here other than 1. And if I take out an x squared, I have nothing in common, right? Between the two groups. Everybody see that? Let me write that out real quick. It's not going to work. But if I take out an x squared, leaving me with x plus 3, over here, all I've got is 1 times 3x plus 2, and I can't do anything with that. There is no common factor, right? So I can't proceed with grouping. So what could we do? Well, we could try to rewrite this thing in a way where I maybe could group. So one thing maybe I could do, and how would you see this? Just by practice. I mean, this is just by doing lots of math. But this stuff, you get better at this stuff, I promise you. So we could break this term right here up into, how about if we broke that up into a 2x squared plus x squared Why might we do that? Okay, we might do that. And here's kind of what maybe goes through your head a little bit. If these were the last 2 terms of a simple quadratic, right, where the coefficient of a is 1, we would have magic numbers 1 and 2, wouldn't we? Right, everybody see that? If I were just to, for example, split this right down there, then this is an easy one to factor, right? 2 times 1 is 2, and 2 plus 1 is 3. Everybody see that? So we could, I don't know which one you would call the blue and which one you'd call the red. They're just really, in this case, there isn't a clear greatest common factor in leftover. We're just breaking it apart. Let's start over on the left side maybe instead. What is the greatest common factor of those two? X squared. What's left over? Okay, and then here's my plus. Oops, sorry, wrong plus. This is my plus right there. And then if I break this into factors, well, one of them is going to be an x plus 2, so let's make that red. And the other one's going to be x plus 1, right? Everybody agree? See that? Okay, so that does work, doesn't it? Now I do have a common factor in each group, the red factor, right? That's hard to see, but you kind of get an inkling how maybe if you thought about this a little bit, that you could think possibly that would work. If you see something like numbers like this that would work as magic numbers, then you always know, okay, I do have the option of at least trying to split out this x squared term, right? And it's not always going to work, but it might, like it did in this case. So then if I pull the x plus 2 out front, What am I left with? Okay, I'm left with x squared plus x plus 1. Okay, and are there magic numbers that multiply to 1 and add to 1? No. So we're stuck, I mean, we can't go any further, right? This one won't factor. But that would be the end of the line for us. Okay. Does that make sense? Okay. If we were solving this, so this was all set equal to 0, we'd get one solution, x equals -2, and just think about the discriminant really quick. B squared minus 4ac. That could be positive or negative. Yeah. 1 squared minus 4 times 1 times 1, it's negative, right? So no reals from that one. Okay. Does that make sense? All right. Tell you what, we don't have Chromebooks anyway, so I'm just going to show you one more little thing. And this is not in the book at all. But this is something I want you guys, I won't do this for the other classes, it's something I want you guys to be aware of. How would we do a problem like this? In fact, I'll just go ahead and take it from your next assignment. Okay, what about something like that? What if I had what about a problem like that? How could we solve that? Okay, we could isolate x, right? But we're not quite there yet with how to deal with that, right? I mean, it's not. I could show you in 10 minutes and you'd be fine with it, but we'll deal with that more officially later. So, is there a way we could factor this? There is. There is a way we can factor this. There is a pattern that this fits. Let me tell me what the pattern is. Say it again. We don't have a difference of fourths, but we do have something else that might work. What's it going to be? Difference of squares. I could make this into a difference of squares, couldn't I? Okay, this is what I would call a quadratic form. It's really a quadratic factoring pattern, even though the polynomial isn't quadratic, right? Because I could write this as something squared. Gosh, come on. Something squared minus something squared. So what's the first something going to be? Yeah, what squared is x to the fourth? Well, x squared is, right? So a is x squared. What's b? Okay, so we could follow the pattern. Let's remind ourselves real quick, what is the factoring pattern for a difference of squares? Okay, so we'll just split that up, right? We'll split that up into a plus b times, a minus b. And a is just x squared and b is 4. I don't really need those parentheses there, do I?
Right. Negative form?
No. It's a plus b, that's a and that's b, right? Times a minus b, right? So we've just dealt with it as a quadratic. Well, now we've got it broken into smaller factors. We just look at each of those individually and ask, can we go further? Can we go further with that one?
Yes.
What do we do? Can we? No, that's a sum of squares, doesn't exist, right? So that one we're stuck with. What about this one? That's another difference of squares, isn't it? That's x squared minus what squared? 2 squared. So this is gonna split into x plus 2 times x minus 2, and this one can't go any further, because it's a sum of squares, right? Okay, so what's the trick? Well, there's nothing there you didn't already know. It's just using an old pattern on a new kind of polynomial, right? In fact, this would have worked. I could have made this look even harder. I could have done something like, for example, I mean, it's not really harder. What if I had said this?
Oh, goodness.
Okay, I could do this as a difference of cubes. That's fine. I could do it as a difference of cubes, or I have another choice. I could make it a difference of squares too, right? I could make this x cubed squared minus. Yeah. Hey, listen. This is way too loud. We got a minute here. Focus, please. Everybody see that? So I could do this, right? And then I just know if I chose to go this route, I have a squared minus b squared, so I'm just going to get a plus b, right, times a minus b, and I can deal with both of those, right?
Yeah.
Okay, make sense? Okay. Oops. Yeah. Okay. All right.
Maybe we'll drop this iPhone off.
Yeah. Go ahead.